Alright. Oops, wrong color. Energy and simple harmonic motion. We're going to start the discussion with a specific discussion of energy for simple harmonic oscillators mass on spring. And if we have time at the end, which I think we will, I'm going to talk very briefly about how it will relate to pendulums, because the relationship more or less still holds for pendulums as well, just with a slightly different form. Alright, so if we want to talk about the total mechanical energy, it is a sum of the kinetic energy plus the potential energy. In this context, the kinetic energy would be 1/2 mv squared, and the potential energy would be 1/2 kx squared, because we're talking about a mass on a spring type situation. So we'll have our mass, and it's connected to a spring with some spring constant. Alright, what we had previously figured out is that the position follows a function something like a cosine of omega t plus the phase, where we found omega to be the square root of k over m. As a quick reminder, this is coming out of a differential equation that looks something like a plus k over mx is equal to 0. So minus kx is equal to ma, and rearrange it, and we get our solution out of it. If we take the first derivative to find velocity, we're going to have a minus a omega sine of omega t plus the phase. So we can actually write out the total energy pretty directly here. 1/2 m, the velocity squared, so minus a omega sine omega t plus phase, the whole thing squared, plus 1/2 the spring constant, times the value of x, which is a cosine of omega t plus the phase. Whole thing squared. Alright, if we simplify this out, we're going to have 1/2 m omega squared a squared sine squared of omega t plus phase plus 1/2 k a squared cosine squared omega t plus the phase. Now you may be looking at this and thinking, oh, we've got a sine squared and a cosine squared of the same thing. Ooh, that's pretty lucky. If the stuff in front was the same, we'd have a sine squared plus a cosine squared, and trigonometry's most basic identity says that's equal to 1. So let's see if we can turn it into that. And of course, we can. It depends on the use of omega. Omega is the square root of k over m, so squaring it gives us k over m. And as soon as we cancel out what we just got there, an m over m, we are going to have the same factors. So the total energy of a mass on spring system is 1/2 ka squared times the quantity sine squared omega t plus phase plus cosine squared omega t plus phase. And that gives us the total energy at all times, is 1/2 ka squared. So if we're looking at what's happening to energy versus time, it's actually staying constant at 1/2 ka squared. If we look at what's happening with the potential energy, it's going to be following a sine squared function. And if we look at what's happening to the kinetic energy, it's going to be going opposite that as a cosine squared function. And k plus u is everywhere equal to that same total energy. Cool. So essentially we have some quantity of energy. It's like an amount of water, and it's sloshing back and forth first being all potential, then being all kinetic, then back to all potential. And you've seen other things that work like this in physics. And the most obvious example, you may have seen something with a pendulum that works like this. Oscillation back and forth between the energy in two forms. So for a mass on spring, we get this. But we can talk briefly about what happens with a simple pendulum. At first, it doesn't really look like it's going to be the same. The kinetic energy is easy enough to talk about. 1/2 mv squared, or if you prefer, in this case it's better, 1/2 I omega squared. I, for a simple pendulum, is just the moment of inertia of the ball on the end, so it's just m times the length of the pendulum squared. The potential energy is a bit more interesting because the ball would be down here initially, and then it's risen above that point. So we actually care about this delta y. So we'd have an mg delta y. The delta y, if we think about it carefully, is equal to the length minus the length times cosine of the angle we're at. Alright, a simple pendulum is the other huge example of this type of system. So let's try and wrap this up quickly. It's kind of entertaining or interesting. Alright, so mg, the L can be factored out, 1 minus cosine of theta. So the total energy would look like 1/2 ml squared times the angular speed squared plus mgl, 1 minus cosine of the angle we're at. This is not looking super hopeful yet. We haven't covered simple pendulums yet, but it's going to turn out that the angle can be rewritten in pretty much the same way as we wrote the position. And I'm not going to talk too much about what omega is right at the moment. The omega that's inside here is distinct from the one that's outside. They are two different things. The one that's outside would actually be the first derivative, where we'd get a minus omega theta naught sine omega t plus phase. And if we put these in, you can see that it's not looking very good for us. Sine squared omega t plus phase, mgl, 1 minus cosine of theta. Well, I don't want to put that theta in because that's going to be a nightmare. But we do know theta is small, and omega squared will be equal to g over L. That's something we'll find out when we do simple pendulums, which is coming up soon. Alright. 1/2 ml squared g over L, so we get some cancellation in there. Come on, red. Come on, red. There we go. Alright, we've got to handle what's going on here if we want to show that it still works the same way. And it turns out we can expand the cosine theta. If theta is small, it's going to be approximately 1 minus 1/2 theta squared. And I do want to wrap this up because this is kind of extra. Let's see, mgl, if we have a 1 minus, last step for the moment, mgl sine squared omega t plus phase, plus we have an mgl. We get these canceling out. We've got a 1/2 theta squared, but theta squared is going to be theta naught squared. I just noticed a problem. This should have been coming down the whole way through. So theta naught squared cosine squared of omega t plus phase. Alright, so now you can see we've got the same leading factors out in front. We've got the sine squared, cosine squared. So for a pendulum, 1/2 mgl, the release angle squared. So pretty similar for the most part. Alright. The general gist, though, regardless, is that the kinetic plus the potential is always equal to the total. So we can still work things out for a pendulum even if we don't have the details. Alright, again, this first part up to the energy of a mass on a spring is the main focus here. You may find this idea here, particularly that small angle approximation and expanding out the cosine, will get us out of trouble. Of course, you have to know about expansion of functions, so you've got to have had your second semester calculus for that. Alright, that's it for this video. We'll come back next time with a problem.